So hi everyone. So let's start the next topic, and which is the most important topic in this operating system. All right. The name of the topic is interprocess communication and synchronization. So when I say interprocess communication, what do I mean by interprocess communication? By saying interprocess communication, what I mean is there will be multiple processes. Let's say this is process 1, this is process 2 and process 3. Okay. So the communication between each of the processes. Okay. So the communication between process 1, process 2 and process 3. Now you may think why on the first place multiple processes will communicate. So let me try to give you a real world examples. So let's say you are making a live video recording. Okay, this is your mobile phone, you are making a live video recording on YouTube or maybe Facebook or maybe on Instagram. So just to help you relate very easily, that is, let's say there is a process. So the responsibility of that process is record the video, pre-process the video and put the video in a particular place in your RAM. All right. And there will be another process. Let's say that is process 2. So this pre-processing shooting of the video was done by process 1. And there is another process 2. The responsibility of process 2 is to take the chunk of these videos, okay, and transmit it to the server of the application. It might be server of YouTube, or it might be server of Instagram, or might be server of Facebook. All right. So two processes are communicating with each other to make the live streaming feature work. All right. So let me try to give you one more example. So let's say there is a process, okay, there is a process. The purpose of this process is to generate some files. Okay, let's say this is process P1. Okay, so this is generating file 1, then file 2, then file 3, then file 4. Now the responsibility of process P2 is go to the directory. Okay, these files are put in a particular directory. Go to the directory, see the available files, all right, and upload these 4 files or available files into some database. All right. So if you see, in multiple cases, multiple processes will end up communicating with each other. So when there is no communication between multiple processes, then things are very simple. But when there are communication between multiple processes, then multiple things may go here and there. We should be very much aware of those cases. Okay. So main purpose of this inter-process communication and synchronize is to teach you how multiple processes can communicate and how will you be enabling multiple processes to communicate with each other seamlessly. Okay. So this is the full form of IPC, that is inter-process communication. All right. Fine. So as I have told you, sometimes multiple processes may need to communicate with each other for different purposes. All right. Just to give you real world analogy, one more. So let's say you are there and you are calling one of your friends. Okay. So what you are doing is you are talking to each other. You are saying something to your friend is saying something to you. So you are a process, your friend is a process. Okay, and you both are communicating with each other. So this is inter-process communication. So you have a process that generates log files. This is the example that I showed you. All right. Another process is there which is uploading those logs files to some database. All right. So P1 will be writing those logs files in a directory, and from directory this process P2 will read those log files and will upload those log files to a particular database. So two processes are communicating with each other. Okay. This is one of the examples, and this is a streaming application example that I have already told you. Let's say you are on Facebook Live or YouTube Live. Okay. So one process responsibility is take videos from your camera and store in a particular place in your RAM. Okay. And the second process is responsibility is to read those data and send it to YouTube or Facebook server, whichever application you are streaming to. All right. So here also, if you see, multiple processes are communicating with each other. All right. So in real world, there will be multiple thousands of places where multiple processes, let's say P1 and P2, then P3, multiple processes may need to communicate with each other to deliver you the end-to-end experience. All right. Just like if I take this example, the end-to-end experience is streaming the live video in Facebook or YouTube or Instagram. All right. So as I already told you, as long as there is no communication between processes, we are good. And why we are good? So I will explain you those scenarios which may go here and there when multiple processes communicate. Once you understand that, then you will be able to understand why when there is no communication, then we are absolutely fine with that. We don't have to do any extra brainstorming over there. Okay. So as I told you, the moment they communicate with each other, the problems start arising. Alright. So we will be seeing why the problems start arising. Alright. So now let's start how a process, how multiple processes communicate with each other. So there are basically two type of ways in which multiple processes can communicate with each other. So one is pipe mechanism, another one is shared memory. Alright. Here let me give you a very brief on pipes. So let's say you are writing your paper. Okay, let me write it down. Let's say this is your exam paper. Okay, this is you, this is your friend. Okay, so you are writing some paper solutions, your friend is also writing some solution. Okay, but let's say your friend has asked help from you for a particular question. Let's say this is question number 9. So he has asked you whether you can help him or not. Okay, so what you have done is you have taken an extra sheet. Okay, and in that extra sheet, what you have done in extra sheet, you have written the answer of question 9. All right, and you have passed this extra sheet to your friend. What your friend has done is your friend saw, oh, this is the answer of question number 9. Seeing that answer, your friend has also copied that same answer under the question number 9. Okay, so this is how pipe mechanism works, and there will be common pipe kind of thing. All right, let's say this is a pipe. So what happens is there is a process P1, there is a process P2. P1 writes data into this pipe. All right, now process P2 reads data from the pipe and saves the data. Whatever P2 has read from the pipe, it saves the data in his own memory. All right, so what will happen? P1 does the write operation once. Now P2 reads the data from pipe. Okay, let's say P2 has read that x equal to 5. Okay, so P2 has a copy of x, and now after reading this x equal to 5, P2 went and written x equal to 5 in its own space. All right, so this is how pipe works. So over here I have explained. Let's say this is the pipe, this is process P1, this is process P2. So P1 will keep on adding data in a particular, okay, P1 will keep on adding data in a particular space as in this pipe. Okay, in RAM. Okay, where this pipe is present, this pipe is present inside the RAM. So what will P2 do? P2 will keep on consuming data from this pipe. All right. So usually this is one directional and slow. One directional as in, so P1 will always be writing something on the pipe and P2 will always be reading from the pipe. And why it is slow? It is because P1 sends the data, P1 writes the data over there. Now P2 comes, P2 reads the data, and P2 copies the data whatever it has read earlier into his own space. So there is one more write operation. So there is a write operation first that P1 does, then there is a read operation that P2 does, and over there inside P2, P2 makes another write operation. Alright, I hope this is clear. P1 sends its count variable. Let's say there is a count variable and there is also a count variable. So what happens is, let's say count equal to 5. So P1 over there inside pipe, P1 writes that count equal to 5. So P2 comes, P2 sees, oh, inside the pipe count is equal to 5. P2 has read the value of count. Now P2 goes and writes on its own space that count equal to 5. Alright. So P1 sends its count value to pipe. P2 reads the count variable from pipe and copies it into its own count variable. Alright. So that is how pipe enables processes to communicate. Alright. So just the example I told you. So you are in the exam hall. This is you. Your answer sheet. This is your friend's answer sheet. All right. So whatever you have written on answer sheet, you write on a question paper or some other sheet. Okay. Let's say there is a sheet. Okay, and pass that sheet to your friend. What your friend does? Your friend. Okay. Let's say this is a sheet. You have written everything in your sheet, and this sheet is passed to your friend. Your friend comes and reads the whatever answer you have written in the sheet. Friends copies it into its own sheet. All right. So that is how this pipe communication works. So let me try to give you some real world analogy. So let's say there is a 2 BHK flat. Okay, and one friend stays in a room 1 and friend 2 stays in room 2. All right. They have two mobile phones. Okay, and only one charger that they use. But let's say one day they had a fight. Alright, as a result, friend 1 is not talking to friend 2 and friend 2 is not talking to friend 1. So now this charger cannot be placed inside room 1 because in that case this friend 2 will not be able to access the charger. Similarly, this charger cannot be placed into room 2 because then this friend 1 will not be able to access the charger. Then what is the solution? The solution is the charger can be kept inside the hall room. Whenever this friend one requires the charger, he can go to the hall room, he can access the charger and he can put the charger in the hall itself and come back to his room. Alright. Then when this friend 2 requires the charger, then this friend 2 can come to the hall, can use the charger, okay, and he can keep the charger in the hall and he can go back to his room. Alright. So here what we have seen is, even though two friends have their separated rooms, but there is one shared space, that is this hall room. So far you understood this hall is the shared memory, and inside this shared memory, what is something that we put? That is a charger. And what is this charger? This is shared resource. Alright. So if I try to map these two operating system concepts, there are multiple processes. This is process 1, this is process 2. In this example, this is friend 1 and this is friend 2. Alright. They both of them are having some shared space. Alright. And this shared space is containing some shared resources. Alright. Let's say this is shared resource. So P1 can access this resource and P2 can also access this resource. So now if I ask you how process 1 and process 2 communicate with each other, they communicate with each other by this shared space. Alright. So if you compare this shared memory and the pipe, you will find that the shared memory approach is much more flexible than pipe, because pipe was one directional, always one process will write, another process will read. But in shared memory, one process can read and write, another process can read and write. Just like P1 can read and write this shared resource, P2 can also read and write this shared resource. So the shared memory is much more flexible compared to the pipe. So the next point is, so this shared memory approach is very much fast. And why is that? There is no concept of copying. So if you remember the pipe concept, what happened in the pipe concept? So let's say there was a process P1, there was a pipe, okay? P1 is writing some value in the pipe. So P2 comes and P2 reads the value from the pipe and stores that value in his local space. Alright. So P2 is copying some value from the pipe. So here in shared memory concept, we do not do such copy. Both of the processes, I mean process 1 and process 2, both of them refer those resources in the shared space. So they read this shared space and they write also on the same shared space. Alright. So there is no concept of copy. As a result, this shared memory concept is very much faster than pipe. Alright. So if you come to the concept of shared memory, where this shared memory is kept, this shared memory is kept inside the RAM. Alright. So that P1 and P2, both of these two processes can access. Like here I have taken the example as charger, and this example can be water bottle as well. Alright. So let me go to the next part. Okay. So what I have written is, each processor having their own memory, we all know. Alright. This is a space for P1, this is a space for P2. So P1 cannot access memory that is allocated to P2 and vice versa. Alright. So P1 cannot access the memory that is allocated to P2 and P2 cannot access the memory allocated to P1. And that is why while communicating, they maintain the common shared space, so that P1 can refer this shared space and P2 can also refer this shared space. Alright. So two processes communicate through shared memory, that I have already explained, because they cannot access private space of other processes. That is what I have just explained. Alright. So this room 1 guy cannot access room 2, the room 2 guy cannot access the room 1, that I have explained that analogy. Alright. So that is why they keep commonly used things in hall, like mobile charger or water bottle. Alright. So let's move to the next part. So this is the place from where the original game starts. Alright. So let's say this is a process, okay, and this is one more process, and let's say this count is the shared variable. All right, let's say this is the count variable. Process P1 is accessing this count variable, process P2 is also accessing the count variable. All right. So what process P1 is doing? Process P1 is incrementing this count variable, if you see here plus plus, and process P2 is reducing the value of count by 1. Alright. So if you run one time P1 and run one time P2, count value, the value of the count should not be changing, because process P1 is incrementing and process P2 is decrementing. Alright. So say count is placed in shared memory. Okay. So this is dedicated space in RAM, that I already explained. Now we will be seeing how things can go here and there when there are multiple processes who are accessing a common shared space. Now you will get to see the problems, okay, and why this interprocess communication and synchronization chapter exist. All right, so let's move forward. So I have explained this process 1 is doing incrementing operation and process 2 is decrementing it. So this is the count, all right. Count is a shared variable, okay. So when you write this count plus plus and count minus minus in the low level, how this count plus plus and count minus minus gets executed. Now let's see that part, all right. So when this process P1 comes to this line and sees, oh, I am supposed to do count plus plus. What P1 does is P1 breaks down this instruction into three more instructions. Similarly, process P2 comes, sees this, oh, I need to do count minus minus. And what P2 does, P2 breaks down this count minus minus into three more instructions, alright? And these are the instructions. So, what are these? This count value is loaded into this register. This register is getting incremented by 1, alright? And after incrementing, this R1 value is again stored in the count variable. Similarly here as well, this count value is stored in a particular register, alright, and after that this value of this register is getting decremented by 1, and again after decrementing this register value is getting stored in the count variable, alright. So that is how this count plus plus operation takes place and count minus minus operation takes place, okay. So once again, yes, so let's assume, so initially count is equal to 0 with initialization, alright. So let's say this is the order. First P1 is executed, then P2 is executed. So when this P1 is finished, then the value of this count becomes 1, and when this P2 finishes, then count becomes again 0, because this is 0 plus 1 and this is 1 minus 1. Alright, so this is incrementing by 1 and this is the decrement by 1. So far there is no issue. So here first P1 took place, then P2. Alright, so after P1 this count value became 1 from 0, and again when P2 executed, the value of count became 1 minus 1, that is 0, alright. Again if you do like this, first P2 then P1, so after finishing the P2 the count value becomes 0 minus 1, that is minus 1, and after finishing P1 the value of count becomes minus 1 plus 1, that is 0. So in both the cases the final value of count is consistent, which is expected, alright. So the special thing that to notice is first P1 completely executed, then P2 executed, and here also first P2 completely executed and then P1 executed. So there was no concept of preemption, alright. But when things start going wrong, let's see. So let's say you are in a preemptive multitasking system. So when the moment you are in a some preemptive multitasking system, that means when you are executing process P1, okay, in between any place, this P1 can get preempted and P2 can get scheduled. And here also, when you are scheduling P2 first, at any place, this P2 can get preempted and P1 can get scheduled. Alright. So where processes switch very fast, a process may get preempted anytime, alright. So whenever P1 is running, there is no guarantee that once P1 is finished, then only P2 will start, or in this case there is no, sorry, and in this case there is no guarantee that once P2 is finished, then only P1 will get started. So in a preemptive multitasking system, at any point of time one process can get preempted and another process can get scheduled. So when we are into this preemptive multitasking system, how things can change, let's see, okay. Before we go into the next part, let me give you some more context, all right. So processes maintain their own set of register values, all right. Same, I will explain. Same register may get used by multiple processes because register at CPU level. Okay, fine, let me explain it. So if you come to this point, if you come to this point, this count variable is stored in a particular register, that is R1 for this example. So this R1 is not attached with a particular process, that is P1, because count plus plus is in P1. So when P1 is getting executed, P1 stored this count variable into R1, and this R1 is not attached with this process P1. R1 is attached with the CPU. CPU is having some multi-purpose registers. You will get to know in more detail when you study computer organization and architecture. But as of now, know one thing, these registers are at CPU level, okay. So maybe this is R1, then R2, then R3 or something like this. Let's say in a CPU there are 3 registers. First R1, then R2, then R3. Alright. So this P1 comes and stores this count variable into R1. Let's say count was 0. So P1 has come and stores this variable of count into R1. So what was the value of count? Let's say that was 0. So 0 is stored into R1. Alright. But now let's say this P1 is preempted and P2 is scheduled. Alright. So when this P2 is scheduled, alright, what will happen is, let's say P2 is also trying to map some variables value into R1. Let's forget this thing as of now. Let's say P2 is having such a line like R1 is equal to, let's say operating system. Alright. So there is a variable called operating system and that value is getting loaded into R1. So what will happen is, let's say operating system is having variable, let's say this operating system is a variable and having value as 5. Okay. So what will happen? This 0 will get overwritten by 5. Okay. So far everything is clear and this P2 is executed completely. Now let's say again this P1 is again scheduled. Okay. So P1 executed till this point, saving the count variable into R1. So P1 knows, oh, I have executed till this point. Now I will have to execute from this line, R1 equal to R1 plus 1, and this R1 has to be stored into count. Alright. But unfortunately, the value of R1 is already overwritten by process P2. So whatever value P1 stored into R1, that is 0, that is lost. So before getting preempted, processes stores what are the values they have written into which register. So before getting preempted, P1 will maintain a trace that, oh, inside R1 I have mapped value 0. When this P1 is again scheduled, so P1 what will do? P1 will directly will not be referring this register R1 because that may have get overwritten. Alright. So what P1 will do? P1 will see, oh, last time before getting preemption, I saw that R1's value was 0. So now I will store 0 in the R1 and I will start the next operations. Alright. So let me get here. Okay. So what I have written is, same registers may get used by multiple processes. Alright. Just now I have explained. Because registers are at CPU level, not at process level. So if I show you the example, this is the same example that I have taken. So before preemption, process keeps a copy of the register values. Okay. The reason I have explained you. So let's say this is process P1, this is the process P2, and this is the register R1. So what has happened is, let's say P1 has written value of R1 as 5 and somehow P1 got preempted. Now P2 has come, P2 overwritten this 5 to 6. So in future when P1 is again scheduled, P1 will be seeing that, oh, R1 is having value 6. So whatever value P1 has already written on the R1, that is 5, that is lost now. So this is something this processes will keep a trace. So in which register what is the value I have seen before my preemption. Okay. So given that, now let's move to the second part. Alright. So when P1 is preempted and P2 is scheduled, it may happen that P2 has changed value of R1 to 6. This is what I have explained here. Alright. When P1 is scheduled again, it sees the value of R1 is 6. So that is wrong, because what value P1 wrote? Initially P1 wrote into register R1 is, that value was 5. Alright. So when this process P2 came and this value is overwritten, okay, so what will happen? This 5 is gone now, 5 is lost. Now P1 cannot find what value? P1 already stored, that I have already explained. For consistency, P1 stores the value of R1 before getting preempted. Okay. So P1 will keep a trace. So what is the value P1 saw inside register R1 before getting preempted? Alright. So that when P1 is scheduled again in the future, then it can run the next set of instructions consistently. So now let's move to the next part. So let me explain the issue in multitasking and preemptive environment. Alright. So process P1 I have already explained you what it was doing, count plus plus, and process to what it was doing, count minus minus. So this count plus plus is broken down into these three instructions, count minus minus is broken down into these three instructions. Okay. And count value is initialized to 0. Now let me show you when things can go wrong. Okay. So let's say process P1 is scheduled at the first time, instruction 1 is executed. Okay. So when this instruction 1 is executed, then R1's value is loaded to 0. Alright. Now let's say after instruction 1, process P1 is preempted and process P2 is scheduled. And when process P2 is scheduled, line number 1 is executed. So that is this one. So now what this line is doing, storing this count variables value into R2. So R2 is having value 0. So what this instruction is doing, so it is storing this count variables value into register R2. What is the value of count? That is 0. So what will be the value of R2? That will be 0. Okay, now instruction number 2, that is this one. Oh, this one is already executed here. So now this instruction 2 of process 2 is getting executed. R2 is equal to R2 minus 1. So after executing line 2, the value of R2 becomes minus 1. So now let's say this line number 3 is getting executed. So what will happen in at line number 3? The value of R2 will be stored in the count variable. Okay. So what is the value of R2? That is minus 1. This minus 1 is stored in the count variable. So 0 becomes minus 1. Now let's say P1 is scheduled again. So this time which line will get executed? Line number 2. Alright. At line number 2, what is happening? R1 is getting incremented by 1. So what was the value of R1? That is 0. So 0 plus 1 becomes 1. So now R2 becomes 1. And now line number 3. Line number 3, what it is? R1's value is getting stored in the count variable. Alright. So what is the value of, oh sorry, this was R1. Sorry, this is R1. So at line 3, what is happening? This R1's value is getting stored in the count variable. So what is the value inside R1? That is 1. Okay. So now this 1 is getting stored in the count variable. So minus 1 is overwritten by plus 1. Okay. Let's write it like this. Plus 1. Alright. So this now P1 and P2 both are finished. So in ideal case, what was the expectation? Count is 0. Okay. You are running P1 and P2 or P2 then P1. In both the cases, final value of count should be 0 because one is incrementing by 1, another one is decrementing by 1. But here if you see at the last this count's value become how much? Plus 1, which is not at all expected. Okay. Okay, let's see one more case. Let's say similarly, let's say, okay, let me erase this tick marks. So one more case is, let's say, okay, let me add one more page. So now let's say I'm coming from the beginning. So count value is 0. Alright. Let's say now P2 is scheduled for the first time. Line number 1 has executed, and after execution of line number 1, what is happened is this R2 register is having the value of count. So R2 will be having value that is 0. And let's say after executing instruction 1, this P2 is preempted and P1 is scheduled. And let's say after getting scheduled, line number 1, line number 2, line number 3, all of these 3 lines are getting executed sequentially. Alright, let's assume that. So what will happen? Line number 1, after line number 1, this R1 will be having the value of count. Okay. So as of now, what is the value of count? That is 0. So what is the value R1 will be having? That is 0. So then comes line number 2. So what is happening is line number 2, the value of R1 is getting incremented. Okay. So the value of R1 will be becoming 0 plus 1, that is 1. So now line number 3 will be executed. What will happen here? So line number 3 will be saying the store this value of R1 into a variable called count. Okay. I mean this same count. What is the value stored in R1? That is 1. Okay. So now let's store this value 1 into count. So count will be becoming 1, not 0. It's not 0 anymore. So now so P1 is done. Now process P2 is again scheduled. Okay. So line number 1 is already executed. Now line number 2 and line number 3 will get executed. So let's see what is the line number 2 of process 2. So the process 2's line number 2 says whatever the value of R2 decrement it by 1. Alright. So what is the value of R2? That is 0. So now R2 becomes 0 minus 1. 0 minus 1, that is minus 1. And line number 3 says store the value of R2 into count variable. Okay. So now so far at before executing line number 3, what was the value of count? That was 1. And after executing line number 1, this R2's value will be stored in count. Okay. So what is the value of R2? That is minus 1. So now this has become minus 1. So if you see in this execution order, the final value of count became plus 1. And in this execution order, the final value of count became how much? Minus 1. Depending on the order of execution. Listen to it very carefully. Depending on the order of executions, if the final value of the variables change, alright, then this condition is called race condition. Okay. So if you can clearly see depending on the order of execution, the final value of count is getting changed. So this is the race condition. All right. Now let's move to the next part. So this is the definition of race condition. So what it is saying is depending on the order of execution, the output may change. So this is called race condition. Okay. So what I have written is synchronization mechanism tries to avoid this race condition. So what is synchronization mechanism? I will come back to this later. Alright, you will get to know it in a more detailed way. Alright, but so far I hope you understood that when race condition comes up, alright, we are having inconsistent values. So our target should be to prevent the race conditions. Alright, depending on the order of execution, the final output should not be changing. Alright, it should be the case that whatever execution order you are having, okay, after finishing everything, the final value of a variable should be same. It should not be inconsistent. Alright, so in a single line, whatever the execution order is, the final value should remain same. Alright, so this will happen when we can prevent this race condition. So this is the one of the main purposes of the synchronization mechanism. So far you know what race condition is. Okay, synchronization mechanism you do not know, but you know at least this thing, that we need synchronization mechanism to maintain the consistency. Okay, so let's move to the next part. So if you come to this place, okay, if you come to this code, where is the code? Yes, so this is the process P1 and this is process P2. So both of them are accessing this count variable, which is a shared variable. Okay, and which part of the code is accessing that shared variable? This part. Okay, this part of the code is accessing this shared variable. So the part of the code that is accessing the shared variable is called critical section. What it is? Critical section. So if you go to the definition, I have written here. Okay, so we have a shared space. In that example, count is shared variable. So we have a shared space where count is stored. Okay, which is getting accessed by both of the processes. P1 is also accessing count variable, P2 is also accessing the count variable. So the code accessing shared space is critical CS. CS as in critical section. So any program may have non-critical section and critical section part. Okay, so let me give you a visual. Okay, so let's say this is a program. Okay, so there might be, this is say non-critical section. Okay, so this is not critical section. Let's say this is critical section. Let's say this is non-critical section. Okay, let's say again this is critical section, something like this. Okay, so one program may have sequence of non-critical section followed by sequence of critical section, again followed by sequence of non-critical section, and followed by sequence of critical section, something like this is how your program may look like. Okay, so let's say this is the non-critical section. All right, let's say this is the non-critical section of your program, and this is the critical section of your program, and this is the non-critical section of your program again. All right, so let me introduce you this synchronization mechanism. I have explained here, right? I have written here this synchronization mechanism. Now let me briefly introduce this synchronization mechanism. High level target of synchronization mechanism is to avoid the race condition. Okay, before this critical section and after this critical section, there will be some piece of code. Okay, and these piece of codes will be responsible for maintaining the synchronization among multiple processes. All right, synchronization as in the consistent state. All right, so multiple processes will communicate, will access the shared resource in a synchronized way. All right, so here this just before critical section and after critical section we put some code. Okay, and these codes are part of synchronization mechanism, which will help us to avoid the race condition and the inconsistent values of the variables. All right, even though we will be seeing in much more detail, but as of now this is a very high level introduction. So before entering into critical section, this is called entry section, and after the just after the critical section, this is called exit section, and we put some code in entry section and we put some code in exit section. Okay, so that this critical section is kept consistent. Okay, so that depending on the order of execution, the final value of the variables stay consistent. Okay, this is the main purpose of the synchronization mechanism. We will be seeing multiple synchronization mechanism in future videos, so this thing will be much more clear. All right, so let's move to the next part. One of the main purpose of synchronization mechanism, so if P1 is inside critical section, all right, no other process should enter critical section. So if you come back to the previous one, I mean previous example, so here this was the critical section. Okay, this was the critical section. So if you break down this count plus plus into these three lines, so this is the critical section and this is the critical section. So if you see, when a process executed line 1, then it is preempted and process P2 is scheduled, and again when P2 got scheduled first, after line 1 P2 is preempted and P1 is scheduled. So it is not the case that once P1 starts doing count plus plus, P1 will not be entering into count minus minus. It is not the case. Okay. So in between this P1's count plus plus operation, P2 is coming into the picture, and P2 is starting its own count minus minus. Okay. So again, listen to me very very carefully. So it is not the case that once P1 starts doing count plus plus, P2 waits and P2 says, hey P1, first you finish, then only I will be doing count minus minus, because we are accessing the shared resources. It is not the case. In between P1's count plus plus, P2 is jumping into and P2 is doing its own count minus minus. Okay. So this is what I have written here. If you come back here, where it is, yes, if you come back here, if P1 is inside the critical section, as in inside the count plus plus, inside those three lines, no other process should enter critical section. In the previous example, when this P1 was busy in doing count plus plus, in between that count plus plus, P2 was jumping into and it was starting count minus minus. So this is something we are not expecting. Ideally, once P1 has started doing count plus plus, P2 should be waiting till the point when P1 is done with count plus plus, and then only P2 will start doing count minus minus. And similarly vice versa also. Once P2 starts doing count minus minus, once P2 is done with count minus minus, then only P1 will jump into and will do count plus plus. Alright? Because count plus plus or count minus minus, maybe plus plus and minus minus, these two lines are accessing the shared resource. So going forward, this part will be much more clear. Let me explain you one more thing. So why do we even need this synchronization mechanism? We need synchronization mechanism because there will be inconsistencies in multitasking and preemptive environment. Okay. Now the question is, why do you even need this preemptive and multitasking system? It is because to increase the efficiency of your CPU. So if I write, so first we wanted to increase the CPU efficiency. Okay, this we wanted to increase. But when we try to increase that, but in between we have seen that we will have to go for this preemptive approach. Otherwise the CPU efficiency will not be increased. Okay. So in this preemptive approach, we have seen there might be some cases when inconsistencies may come up. So now to solve this inconsistency, we have come up with the synchronization mechanism. So after the synchronization mechanism, we have successfully achieved high CPU efficiency. Okay. But one thing to be cautious is, when you are introducing synchronization mechanism, due to small issue in your code, even a small line can lead to a much more bigger issue than you can think of. Okay. So what may happen? Your CPU may waste lot of time in waiting state, not doing anything effectively, or there is a even more dangerous thing, that is your system may fall into deadlock. But what this deadlock is, we'll be seeing deadlock in much more deeper way. So as of now, just know one thing: deadlock is a state where all the processes are stuck. Okay. None of the processes are moving towards the finish line. Okay. And your system is not progressing at all. Okay. Which is the dangerous thing that can be introduced with the wrong code at synchronization mechanism. Okay. In future videos, we'll be seeing in much more detailed way.